should restart? Yeah. And let's.
Yeah. Want to tell you something?
Yeah.
No, just don't get nervous. If
Just tell me when I should stop.
No. I mean, the thing is, I have this official thing that my students have to look at the exams, and I have to the exams are in my office. I have to give it to my
Don't
TAs.
worry.
So the thing is, I might run out for just a moment, just towards the end. It doesn't mean that you just I will tell Jan to chair it.
But what's a good time for me to stop?
It's actually better if you go a little bit beyond one.
Okay, well, I might not make it because we'll see.
Anyway, just
all right.
don't get discouraged.
Okay. Okay, so ready to go? We got our hands dirty a little bit just now, but now I just want to go back in a little bit more overview style. And I want to go back and tell you sort of from the experimentalist's perspective. They would like to use theoretical predictions. And depending on the process, different levels of approximation are available. But the bulk of what they use are programs that are presented to them in a Monte Carlo form. So I thought I would tell you a little bit about Monte Carlos and also how people try to make Monte Carlos more precise to absorb or take into account higher order predictions. So there are many different Monte Carlos. There's the most commonly ones are Pythia, Herwig, and also Sherpa. In fact, those are the dominant three. I should have put Sherpa up here. And I'll say more about Monte Carlos in a second. Of course, another thing you can do is leading order, which is just Feynman graphs of tree level and square them up. And those are often abbreviated by MEs or matrix elements. But it's useful to try to fix up Monte Carlos by incorporating the information from leading order. And so there's a way of doing this, which I'll try to sketch briefly, and matching the leading order matrix elements to parton showers. So that gives you some of the benefits of both techniques. And those are commonly now incorporated into different Monte Carlos. So Sherpa is a full-fledged Monte Carlo framework, but it was also one of the first to do this matching between leading order and parton showers. But there are many other frameworks for doing that. AlpGen was another early implementation of these algorithms, but they're basically inside all of these main Monte Carlos by now. But you may want to go beyond leading order. And so you can, first of all, usually when a new process is calculated next to leading order, it's first done at the parton level, like leading order. But for many purposes, that's not as useful to the experimentalists. And so then there's a procedure of matching the next to leading order results to showers. And it's trickier than leading order, but it's also becoming pretty standard by now. And then at some point you get to programs, and these are some of the earlier ones, but there are many more now, of next to leading order matrix elements. And actually I should have updated this because there are now, for simple processes, Monte Carlos at next to leading order. So what is a Monte Carlo? Well, it's based on the fact that there is this universal behavior in the collinear and soft limits. And it's an attempt to iterate that behavior probabilistically. So it at least iterates certain double logarithms that include both the collinear and the soft behavior. And there is a certain amount of debate over how much more you get than that, and attempts to improve this accuracy. But the basic idea is that you start with a hard process, and it generates some initial outgoing partons, and then you shower them with a probability distribution that is based on the leading order Altorelli-Parisi splitting kernels in the time-like case. And you also do a backward evolution for stuff that happened before the hard process for space-like splitting in the initial state. And this radiation is approximate in the sense that it's really only guaranteed to be accurate when things are very collinear and or very soft. And that's why it's often useful to patch it together with fixed order matrix elements, which model hard radiation a lot better. But the advantage of the Monte Carlos is in this approximation, you can evolve this shower and generate a large number of quarks and gluons in the final state. And those give a more detailed, fleshed out picture of what a jet looks like. And then you need to have some models for hadronization, as I sort of discussed briefly before, and also models for how the hard event, the things beyond the hard scattering event from the remnants of the protons, the spectator interactions. And at the end of the day, you get a complete hadron level description, and that's very important for the experimentalists because the experimentalists know their detectors aren't perfect and they need to simulate the detectors using realistic hadrons, configurations of hadrons entering them. But the normalizations of event rates are usually not that reliable for the basic Monte Carlos, which is the reason for trying to combine them with higher order matrix elements. So here's a picture of how you might think about a Monte Carlo process. You would calculate some lowest order process, and it would generally be the simplest process, like 2 goes to 2 scattering of some type, quark gluon scattering here. And you would generate an event based on a probability distribution drawn from this process. But then you would take and ask about a probability for this gluon branching, and that uses that splitting kernel. But there's also a factor, and for example, we had this splitting kernel here that we derived, and you would feed that in here and generate some probability distribution according to this. So if z is near 0 or 1, it would be larger to take into account the soft enhancements when this branching is asymmetric, and it would be smaller when z was of order 1/2. And then you also have to, the total, the dependence on z is carried here, and the total dependence was integrating over z, and you put in some cutoff, because when z goes to 0, then this virtuality would go exactly to 0, and you don't want that. So there's a cutoff on the endpoints of z that's enforced by some theta function here. But you also need to have a no-splitting probability called a Sudakov, and that involves an integral over this splitting probability from some high scale q squared, capital Q squared, to some low scale q squared. This factor gives you a way of rolling the dice, and you generate random numbers, you compare them to something related to this Sudakov, and the output of that comparison tells you at what scale this branching takes place in a given process. So you generate it randomly so that overall you get an appropriate distribution in this next branching. And this depends on alpha s as well. So early branchings might be a little rarer because alpha s is smaller. And then as you go to lower scales, alpha s becomes larger and the branching develops faster later on. And you have to apply these Sudakovs to all the final state partons and ask which one branches, and randomly you order things in this variable q squared. But you also have to do backward evolution for gluons that may have come from a proton back further. And you keep doing this. And at the end of the day, you generate at low q squared a number of partons, which would actually be much larger than the number I've shown here, but I got lazy. And then when you have reached a q squared close to the hadronic scale of a few GeV squared, you assign colors to these, well, you actually usually do all of this showering in a color ordered way in the large N approximation. And so then you split gluons, and they have double color, and you, using the color flow, you either decay clusters that are color singlet, or you have some string model where you have a way of splitting the strings into hadrons. And so then you get a model for where the hadrons are going. And you produce hadrons with given momentum distributions. And you usually include a lot of parameters here that can be tuned by the experimentalist to try to match the relevant data for these distributions. And by the way, I didn't do this right, so if you're interested, you can try to find a mistake I made here. Well, it's actually just a color flow mistake. I took a quark out of this proton, so this thing isn't a color singlet anymore. And it should have been neutralized by some other triplet going the other way at some point. So now going back to the even more primitive approximation, there's leading order matrix elements themselves that are based on the sum of all Feynman diagrams in QCD, and of course not just QCD, but QCD coupled to the rest of the standard model particles like W's, Z's, and Higgses, and so on. And this generates hard radiation better. And so it can get kind of event shapes somewhat reliable, but the normalizations are pretty uncertain at leading order. Could be 100% uncertain. And also, when you do a leading order process, a jet is modeled by a single parton. And so there's sort of no information about how the jet depends on the jet algorithm, on some size of the jet. You just don't get any of that right at all. Nevertheless, it underlies everything else you do. So there are a lot of programs that can produce these tree-level cross-sections for very high multiplicity. And you need to estimate a cross-section, you need to collect a sample of many events in order to do a Monte Carlo integration over the phase space. And so you have to do this very quickly. Some of these use Feynman diagrams. Most common now is recursive or iterative organization. But as far as I know, most of the techniques are fairly similar to what are called off-shell recursion relations. And these were developed by Behrens and Gila back in the 80s. And I don't think that the BCFW relations are used quite as much for this. It's more based on a little earlier recursive approach. So then there's this issue of trying to get the best of both worlds, to have both higher order matrix elements, not just 2 goes to 2, but 2 goes to 3, 2 goes to 4, and so on, at the same time that you have a Monte Carlo. But this brings up a question of double counting, because if you have an event like this, the question is, was this produced by a splitting in the Monte Carlo, or was it produced by the fixed order matrix element? And depending on where you are in the phase space, you should get sort of one answer or the other, but you shouldn't double count things, or else you'll get the wrong result. So there are some frameworks for doing this matching, and I don't want to go through them in any detail, partly because I don't understand them in any detail. But you can separate which regions contribute by using some kind of a jet cluster algorithm variable, and you invent some fake sort of size of a jet and you use that to determine which events come from where. There's a nice picture that kind of illustrates the double counting question by Naj and Soper. So you might have a probability that came out of a Feynman diagram or BCFW or other kinds of exact matrix element or exact tree level matrix element. So I mean exact angular dependence, but tree level for the 6-point amplitude. That is 2 goes to 2, but 2 goes to 4 rather. And then you might also have a Monte Carlo simulation that starts at n equals 4. And then this shows it evolving with q squared. And there's a Sudakov factor that you would normally use just in the Monte Carlo to determine when this splitting occurs. And then you'd have more Sudakovs to the next one. But contained within this is a splitting configuration, which is also buried inside this matrix element in the collinear, in the appropriate double collinear limit. So you should divide out by this process in order to avoid double counting inside here, this contribution as well. So this is a very schematic picture of how you can try to implement these matching algorithms and generate events that correspond to the matrix element in wide angle limits, but also generate realistic looking jets. So there are various schemes that were implemented to do this, and quite a while ago people compared a number of these schemes, and they were getting reasonable agreement for some types of distributions, but other distributions, the different methods gave somewhat different results. Now this is fairly old, so I think there's been a little more convergence since then on exactly what to do. But there is still an art form. So next to leading order matrix elements, that's been a big industry. This is a little bit old, but basically you get much more reliable normalizations, good to maybe 10 or 20%, depending on the processes. You can also get event shapes somewhat reliable, but there are definitely cases where you need to do better. As I was mentioning earlier, if you take a color singlet object like a W or a Z or a Higgs, and you ask what happens when its momentum goes to 0, that is some question you cannot answer strictly within fixed order, and you need to do resummations. And nowadays, though, the one-loop amplitude technology has been vastly improved, and so you can actually get next leading order results out for processes with up to 5 or so final state objects. And then you can go and combine those next to leading order results with Monte Carlos, and so that there's a generic framework or idea called Monte Carlo at next to leading order. There's also a specific program, MC at NLO. There's also another framework that's commonly used called POWHEG. And this is just an example of an output from one of these programs. This is, in this case, you're making top quark pairs, TT bar, and you're looking at their transverse momentum. And when the transverse momentum is very large, what you're supposed to see is that this curve in black converges to the dotted line, which is a fixed order calculation. But when the transverse momentum of the TT bar pair becomes much smaller than the TT bar mass, which is 350 GeV, then the NLO result is very singular. And this is a Monte Carlo resummation of that distribution, which recognizes that that region is controlled by soft gluons, and there should be sort of a Sudakov suppression in that region. So the Monte Carlo MC at NLO rolls that off and gives you a smoother distribution. So this is just typical of how you have a transition between a fixed order calculation and a Monte Carlo regime, a region where the Monte Carlo controls things. More recently, people have been calculating NNLO for quite a wide range of processes with first one object in the final state, like W, Z, and Higgs. But nowadays, things like double vector boson production have been done. In fact, a lot of the NNLO progress for 2 goes to 2 was made possible by understanding these Goncharov polylogarithms, because they come into the matrix elements for things like glue goes, or QQ bar goes to WW, and those results have led to much more accurate cross sections. But 2 goes to 3 is still a big frontier. Even at 2 goes to 2, when you have processes with top quarks in the final state, there are pieces of those that are not polylogarithmic, that are elliptic, and as far as I know, they still haven't really been done analytically, but fortunately the kinematics are simple enough that they were done numerically, and you could get enough control. The challenge is to get good control when you have a multivariate process. When you have only a few numbers of variables, you can beat the thing to death. When it's a very large phase space, it becomes a lot trickier. So that's for the future. I actually don't really have that much more to say, so I'm probably going to stop a little bit on the early side. Hope that's okay. I do have a more detailed discussion of NLO calculation, but I mean, I could start it today, but I could also just, I think maybe we should just wait and start it tomorrow. Okay? Any questions?
Don't be shy. Can you describe this matching? So I understand that in this showering, you use the splitting kernels in the probability statement. So
Yeah.
there's a certain loop order which you use there in the splitting kernel.
Well, really you only, in current programs, you basically just use leading order splitting. So it hasn't really been, see, when you go to next to leading order, you will have, if you compute a next to leading order splitting kernel, you can get contributions that come from taking this leading order blob that I described and squaring it or interfering it with the next to leading order term. But then you will also have terms that come from triple collinear behavior. And you have to square these and decide how you're supposed to distribute these events to make it more exclusive. So when you do the parton evolution, it's a very inclusive thing. You only look at one parton with one momentum fraction, and you integrate over everything else. At leading order, it's pretty trivial because of momentum conservation. You kind of know where the other guy is going. But now, at next to leading order, you have a virtual term which sends one parton one way. You have real terms which send 2 separate partons 2 different ways. And you have to also combine it with soft behavior when you move out of the collinear approximation, then things get tangled up with other partons, because remember the soft emission kernel depends on where 2 things are going. So people are working on this, but I don't think there's and pieces of it have been analyzed, but there isn't yet a fully consistent Monte Carlo that really does next to leading order evolution. It's basically all leading order. When we talk about these matchings with fixed order matrix elements, the event rates are being kept at the fixed order level, but the showering is really still being done at a kind of a leading, we call it leading logarithm, because it's sort of resumming logarithms. I don't know.
So this does make sense, even though you
You know, it depends on what you want to get out of it. It maintains the right accuracy for overall event properties, and it gives you some kind of simulation of the exclusive structure of the event. But the exclusive structure is not as accurate as if you could really implement this next to leading order shower. In the end, the experimentalists hope to measure things which are less sensitive to the detailed structure when they're trying to do precision measurements. But they still need to have some idea how the shower affects the structure of the events. Because they don't make perfect measurements, they have to know how events migrate from one bin to another, and things like that, due to their detectors.